Namaste and a very good morning to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about how to build a convolutional neural network using Python. Even before I proceed to demonstrate how to build the convolutional neural network using Python, may I request you to subscribe to my channel, also like and share my videos. In this video, I'll be explaining about convolutional neural network on the very popular MNIST dataset. Now, what exactly is this MNIST dataset? MNIST is simply an acronym for Modified National Institute of Standards and Technology. I repeat, MNIST is simply an acronym for Modified National Institute of Standards and Technology. What is the MNIST dataset all about? The MNIST dataset, remember, is a benchmark dataset which is used in machine learning and computer vision. Now, this is a dataset which consists of a sample of 70,000 grayscale images of handwritten digits. I repeat, this is a dataset which consists of 70,000 grayscale images of handwritten digits. In this dataset, the training data consists of 60,000 images and the test sample size is 10,000. So the overall sample of 70,000 images is split into training and testing. The sample size in the training dataset is 60,000 images and the sample size in the test is 10,000 images. Let's look further into the image characteristics. When you look at the image characteristics, here each image in the dataset is a 28 by 28 pixel image. The images have been normalized to have a fixed size and centered within a 20 by 20 pixel box. Thirdly, the digits range from 0 to 9 and are labeled accordingly. In a few moments from now, I'll display the sample images that are present in this particular data set. When you're building a convolutional neural net, the first thing is to import the necessary libraries. As you can clearly see here, there are a few libraries which I'm importing. The first being NumPy. NumPy is a very popular library which is useful for numerical computations. Secondly, we will need to load the dataset. So we will be using the import MNIST function. This is called from tensorflow.keras.datasets. This dataset comes inbuilt when you install the Keras library. Further, we are also importing the sequential function from tensorflow.keras.models. The fourth line, we are doing a lot of stuff here. Let me just explain this one by one. We are importing the convolutional 2D layer, followed by the max pooling 2D layer, and then the flattening layer. Fourthly, we are also importing the dense layer. These four important functions are basically imported from tensorflow.keras.layers. I want to explain quickly these four items which I've listed. This is mostly useful if you do not have a background in computer sciences, if you do not have a background in statistics or programming, or you're very new to Python. These phrases may slightly intimidate you. So I want to take a couple of moments to explain each of these functionalities. What is this Conv2D? Now, this layer creates a convolutional kernel that is convolved with the input image to produce a set of output features. In other words, when we use the Conv2D, it applies a set of filters to the input image and produces a new set of feature maps that represent different features of the input image. The Conv2D layer is commonly used in CNN for image processing tasks such as image recognition. So long story short, please remember that the Conv2D layer is very popularly used in convolutional neural network models for image processing tasks such as image recognition. The next thing which I want to talk about is the max pooling 2D layer. What are we doing here? This layer downsamples the input image by taking the maximum value within a small kernel or window. I'd like to repeat this. The max pooling 2D layer downsamples. It downsamples the input image by taking the maximum value within a small kernel or window. This reduces the dimensionality of the input, which helps to reduce the number of parameters in the model and improve its performance. The max pooling 2D layer is commonly used in CNN to downsample the feature maps produced by the convolutional 2D layer. So this could be a popular interview question as to what is the purpose of max pooling. So your answer can be the max pooling 2D layer is used to downsample the feature maps produced by the Con2D layer. Next, let's talk about the third important functionality, namely flattening layer. What are we doing here? At this stage, though we are importing the functionality, at a later stage, we will be using each of these functions. The flattening layer, as the name itself suggests, flattens the input tensor into a one-dimensional vector. I'll repeat this. The flattening layer flattens the input tensor into a one-dimensional vector. This is useful when transitioning from convolutional layer to fully connected layer, which requires a one-dimensional input. The flattening layer is commonly used in neural network for image classification tasks. Next, let's talk about the dense function which we are importing. What is the use of the dense function? The dense layer is a standard fully connected neural network layer. I repeat, the dense layer is a standard fully connected neural network layer where each neuron in the layer is connected to all the neurons in the previous layer. The dense layer is commonly used in the neural networks for image classification tasks and other ML tasks. So these are the four important functionalities which we will be using, and it helps to remember what each of these functions do. Last but not the least, I'm also importing the to_categorical function from tensorflow.keras.utils module. Let me go ahead and quickly execute this. So at this stage, what I've done is I have laid the foundation for building the convolutional neural network model by importing all the necessary functions from the appropriate libraries. In the next code, what I'm doing is I'm loading the MNIST dataset. Remember, the MNIST dataset is part of the Keras library. When you install Keras in Python, it comes by default. How do you load this particular dataset? You have to use the load_data function on the MNIST data, and then you can load this particular dataset. When you load this particular dataset, you will be able to capture the x_train. Then you'll also be able to get the y_train. Next, you'll get the x_test object and the y_test object. x_train will have all the features which will be used as the independent variables. y_train will have the dependent variable for training. x_test will have the independent variables or the features of the images, the handwritten images, which will be used as the independent variables. Further, you have y_test, which is the dependent variable for the test data. So these are the four objects that we have loaded at this stage. Now, for the purpose of clarity, what we are doing is at this stage, in the next stage rather, I will be displaying a sample image. To display the sample image, you would need a functionality which is called as IMShow. And this functionality can be activated. This functionality can be called when we import the matplotlib. So plt.imshow is the functionality which allows you to display some of the images. Let me quickly go ahead and execute the second image. Let me show you. This is how the second image appears. You can see here, this is a handwritten image of 4. I know that it is not very clear, but this is how it comes. So we are trying to predict whether an image is a 4 or a 0 or a 1 or a 2 or a 3, or it could be 5, 6, 7, 8, 9. It could be any of these labels based on certain features of the handwritten images. This is one image which I'd like to show. In the next command, what I'll be doing is I'll be showing a sample of images. Let's look at 10 images. Let me go ahead and display the first 10 images. You can just take a look at a sample of 10 images. You can see here, some of the sample handwritten images are 5, 0, 4, 1, 9. It's a bit difficult to recognize 1 here because normally people do not write 1 like this. Our goal here is to train an algorithm so that this machine learning algorithm has sufficient intelligence to read this particular image and say, hey, this is 5, this image is 0, and this image is 4, and the next image is 1, 9, so on and so forth. In the next row, you can see 2, 1, 3, 1, and 4. For the human eye, it is very, very easy to recognize these images. The question is, can we train a deep learning module? Can we train a deep learning model which can easily recognize based on the input features and see which number the image is displaying? Let's now make a move on to the next important step. In the next important step, what we will be doing is what is called as data pre-processing. I repeat, this stage is called as data pre-processing. By and large, for any image classification tasks, we need to perform the feature engineering. There are 3 commonly used feature engineering tasks which I'd like to draw your attention to. The first task is normalization. The second task is to reshape the data. And the third task is to one-hot encode the data. So remember these 3 tasks. First is normalization. Second is reshaping the data. And the third is one-hot encoding. Let me explain this step by step. One question that can pop up in your mind is, what exactly is normalization and what is the purpose behind normalization? Normalizing the data means scaling the pixel values of the image to have a 0 mean and a standard deviation of 1. I repeat, normalizing the dataset means scaling the pixel values of the images to have a 0 mean and a standard deviation of 1. This is a very common data pre-processing step in machine learning, which can help improve the performance of the model. So many times, one question that is asked is, why do we normalize the data? The answer is, this helps improve the performance of the model. When we divide each and every pixel by 255, what we are effectively doing is, we are rescaling the values to be between 0 and 1. So when you divide the number by 255, you are rescaling the value to be between 0 and 1. This puts all the pixel values on the same scale and prevents numerical instability. This also helps the model to converge faster. So these are some of the advantages of normalizing the pixel values. As you can see here, I'm using x_train. I am treating this, I'm asking Python to convert this into a float object and dividing it by 255. I'm following the same strategy as far as x underscore test is concerned and creating two new objects which will contain the normalized scores. The two new objects are x underscore train and x underscore test respectively. Let me go ahead and execute this particular command. I'd like to draw your attention to what are the typical advantages of rescaling. Now, if you're very new to the world of image processing, remember that this is an exercise which we do almost all the times before feeding the image for a machine learning model. What are the three advantages of rescaling? This is a popular question as well in the interview. Here, I'm saying that the first advantage of rescaling is to improve the performance of the model. Second advantage would be that when we rescale, rescaling puts all the pixel values on the same scale, which can help the model converge faster during training and prevent numerical instability. Last but not the least, normalization ensures that the data, in fact, normalizing the data ensures that all the features have roughly the same scale. So these are the three advantages of rescaling the data. As you can see here, in this stage, after normalization, what we are doing is we are reshaping the input data to be 4-dimensional, right? We are reshaping the input data to be a 4-dimensional data. What are these 4 dimensions? The first dimension is the batch size. Second dimension is the height of the image. Next would be the width, and the fourth dimension would be channels. So these are the 4 dimensions which we want the reshaped data to have: batch size, height, width, and channels. Please note that the original input data may be in a different shape or dimensionality, depending on the format and the source of the data. In this case, the x underscore train and x underscore test object are assumed to be 3-dimensional arrays, with the dimension being number of samples, height, and width. As you can clearly see here, we are using the np.expand underscore dimensions on x underscore train. Why are we using the np.expand underscore dimensions? The np.expand underscore dimensions function is used to add a dimension to the input arrays, specifically at the last axis. And therefore, we are specifying the axis value as -1. I'd like to repeat this. The np.expand dimensions, as the name itself suggests, expand dimensions is used to add the additional dimension to the input array. This we are doing specifically at the last axis. The axis parameter specifies the position. The axis parameter specifies the position along which the new dimension is inserted. Since we want to add a new dimension at the end of the array, we use axis equals -1. We are using the np.expand underscore dimensions both on the training dataset as well as the testing dataset for the input features. To give you more clarity on what is the purpose of reshaping the data, I'd like to draw your attention to some of the points that I've highlighted. The purpose of reshaping the input data to be 4-dimensional is to prepare it for consumption by the CNN model. The CNN model is designed to operate in such a way that it expects a 4-dimensional data. The input data in our case was a 3D image. So we are converting a 3D structure into a 4D structure so that I can feed this into the convolutional neural network model. This is the basic expectation of a convolutional neural network model. That is, it consumes the input data in a 4D format, not in another format. A CNN requires the input data to be represented as a 4D tensor with the dimensions of batch size, height, width, and channels. I repeat, the dimensions are batch size, height, width, and channels. Let me explain each of these parameters. What do we mean by batch size? Batch size here refers to the number of training examples that are processed in one forward or backward pass. When we speak about the height, here the height parameter represents the height of each input image in pixels. Nextly, let's talk about the width. The width of each input image in pixels is the third parameter. The last parameter here would be the channels. The number of color channels in each input image. That is, this parameter will take a value of 1 for a grayscale image, and it takes a value of 3 for a RGB channel. So this is about the essence of reshaping the data. We are now moving on to the third step. I repeat, we are now moving on to the third important step under the data preparation stage of one-hot encoding the vectors. We will be converting the labels to one-hot encoded vectors. As you can see here, we are using the to_categorical function on y_train data. What does this do? Let me explain this. The to_categorical function is used to convert the categorical labels into a one-hot encoded vector representation. I'd like to repeat this. The to_categorical function is used to convert the categorical labels into a one-hot encoded vector representation. One-hot encoding is a technique that is commonly used in machine learning to represent categorical variables as numerical vectors, which can be more easily processed by neural networks and other machine learning tools. Simply put, one-hot encoding is a strategy that data scientists use in machine learning to convert a categorical variable as a numerical vector. We can go ahead and execute this particular command. Let me again quickly summarize at a very high level as to what are the three things that we are doing in feature engineering. What we did was to normalize the data. How do we normalize the data? Simply take the input image and divide it by 255. This will ensure that the values, the pixel values, lie between 0 and 1. So this is the first task in image classification, which is to normalize the data. Nextly, we are reshaping the data. We've used np.expand_dimensions to reshape the input data to be 4-dimensional data. The 4 dimensions being batch size, height, width, and channels. Last but not the least, what we are doing is we are converting the labels to one-hot encoded vectors. So these are the 3 tasks that we are doing under the feature engineering for image classification. Now, let's try to understand what exactly is CNN. So far, what we have done is to prepare the foundation for CNN. We have laid the groundwork to build a CNN model. Let me at a very high level emphasize as to what exactly is CNN. CNN stands for convolutional neural network. It is widely regarded as a gold standard when it comes to modeling image data. In this case, since we are talking about handwritten images, this is a classic example of image data, and therefore we will be using a CNN model. There are 5 important points to remember when we are talking about a CNN model. The first being, a CNN is a type of neural network which is commonly used in computer vision tasks such as image classification and object detection. So whenever you're doing image classification or object detection, CNN comes into picture. The second important point here is, unlike traditional neural networks, which are fully connected, a CNN uses convolutional layers to learn the local features and patterns from the input images. So this is one big advantage of a CNN as compared to a traditional neural network model. Let's now talk about the third point. The convolutional layers in a CNN apply a set of filters to the input image, which extract features such as edges, corners, and textures. This is very, very important as to what do the convolutional layers in a CNN model do. I repeat, what is the purpose of using the convolutional layers? The convolutional layers in a CNN apply a set of filters to the input image, which extract the necessary features such as edges, corners, and textures. Let's now move on to the fourth point. A CNN also typically includes pooling layers, which downsamples the output of the convolutional layers by taking the maximum or average value in a local neighborhood. The purpose of using max pooling is to simply downsample the output of the convolutional layers. The last point here is that the output of the convolutional and the pooling layers is flattened and passed through one or more fully connected layers, which use the learned features to make predictions about the input image. So this is the final output of the convolutional and pooling layers. It is flattened and it is passed through one or more fully connected layers, which use the learned features to make predictions about the input image. At a very high level, if you have to understand CNN, you can say that CNN are very, very powerful models, typically used for image processing tasks, and can automatically learn features from raw input data without the need for handcrafted features. Let's now specify the model architecture. This is like the blueprint of the CNN model. Let's try to understand this in depth so that we are very, very clear with each and every concept here. What is happening at this stage is that we are defining the model architecture. This code defines a CNN model using the Keras API with a sequential architecture. The model is composed of 4 layers. There are 2 convolutional layers and 2 max pooling layers, 1 flattening layer and 1 fully connected layer. I repeat, as you can see here, we have a convolutional layer, which is followed by a max pooling layer. We have 1 more convolutional layer, which is again followed by a max pooling layer. Next, this is flattened, and finally, we are passing it through a dense network. Let's try and understand each of these things in depth. When we talk about the very first layer, the first layer is a convolutional layer with 32 filters. As you can see here, 32 here represents the number of filters. What is the size of the filter? The size of the filter is 3 by 3. The activation function that we are using in the first layer is a ReLU activation function. The input shape parameter is set to the shape of the input data. I repeat, the input shape of the input data, the input shape parameter is set to the shape of the input data without the batch size dimension. This layer performs a 2D convolutional operation on the input data with the specified filter size and number of filters, and applies the ReLU activation function to the output feature maps. So this is what we are doing in the first layer. After the first layer, let's now try to understand the second layer in the architecture. In the second layer, what exactly are we doing? We are adding a max pooling 2D layer as part of the second layer. The second layer is simply a max pooling layer with a pool size of 2 by 2. You can see here, the pool size here is 2 by 2. This layer applies a 2D max pooling operation to the output feature maps of the previous layer, reducing their spatial dimension by a factor of 2 along each axis. So the primary purpose of using a max pooling layer is for downsampling. Let's now talk about the third layer. What exactly are we doing in the third layer? This is yet another convolutional layer that we are specifying. In this convolutional layer, with 64 filters, a filter size of 3,3 and a ReLU activation function is used. This layer performs another 2D convolution operation on the output feature maps of the previous layer, generating new feature maps with a large number of filters. So this is as far as the third layer is concerned. Let's now talk about the fourth layer. What exactly are we doing in the fourth layer? In the fourth layer, what we are doing is we're using another max pooling layer. The fourth layer is another max pooling layer with a pool size of 2,2. This layer applies another 2D max pooling operation to the output feature maps of the previous layer, reducing their spatial dimensions by a factor of 2 along each axis. So at this stage, what we have done is we have applied the convolutional layer twice. We have also applied the max pooling layer twice. Let's now talk about the fifth layer. This is the flattening layer. This layer is very, very useful because the flattening layer converts a 2D feature maps into a one-dimensional vector. This layer does not modify the number of elements in the vector, but reshapes the output of the previous layer into a format that can be passed to a fully connected layer. In the last layer, as you can see, which is the sixth layer, what we have is a fully connected layer. I repeat, here we have a fully connected layer with 10 output units. The number of output units that we are specifying here is 10, and a softmax activation function. This layer applies a linear transformation to the input vector, followed by a softmax function that normalizes the outputs to the probabilities. The 10 output units correspond to the 10 possible classes in the dataset. I repeat, the 10 output units correspond to the 10 possible classes of the handwritten images in the dataset. And the softmax function computes the probability of each input example belonging to each class. At an overall level, what this code is doing is that this CNN model performs a series of convolutions and max pooling operations to extract features from the input data and then uses a fully connected layer with a softmax function to predict the class probabilities of each input example. So this will create the blueprint for the CNN model. Once we have defined the architecture of the model, the next step is to compile the model. What exactly are we doing at the compilation stage? In the compilation stage, as you can see here, we are specifying an optimizer. The name of the optimizer is Adam optimization. The loss function that we are using here is categorical cross entropy, and the metric that we are checking for is accuracy. You can use different levels of metric, but I want to keep it simple in this particular video, and therefore I've specified only accuracy. Let's go ahead and compile this particular model. We have covered a lot of ground in this video. As part of the last step, what you can do is we can go ahead and train the model on the training data. We can use a simple function which is called as model.fit, and within the parenthesis, we can specify the input parameters. In the model.fit function, we have to specify x_train, which will give the input features, y_train, which will have the dependent variable. We are also specifying the batch size of 128. Epochs will be 10. We can specify any other number for epochs. Epochs will be the number of iterations. If you specify 100 as the number of iteration, this particular code will take around 20 minutes. So I've kept it very simple by specifying the number of epochs as 10. Finally, when it comes to validation data, we are specifying x_test and x_test and y_test. Let's go ahead and train the model. It would take some time for the algorithm to run 10 different iterations. You can see here, it is still running the first epoch here. We can also specify, we can also look at what is happening to the loss and the accuracy. At each stage, the convolutional neural network will try to burn out the loss. We have to minimize the error and we have to maximize the error. This might take some time to converge. As you can see here, it has only now begun with the second iteration. You can see here what is happening to the loss value as well as the accuracy value. In the first epoch, the validation accuracy was 97.76%, which is not bad at all. If my memory serves me right, the best model achieved an accuracy of 99% on the MNIST dataset. So we are very close to 99%. Let's see if we can build the best model here. If not, we can always go back, revise the model architecture, specify additional convolutional layers and max pooling layers. We can change the hyperparameters, but so far the performance of the model looks promising. I say it is promising because we can look at the validation accuracy in the first epoch, 97%. In the next stage, it has improved to 98%. It will be something to achieve 100% accuracy. Let's hope for the best. Also, let's pay attention to the validation accuracy. In epoch number 1, it was 0.06, which has reduced to 0.05. 5. We are in epoch number 3. You can see here the model performance is improving incrementally. From 0.06, the loss has reduced to 0.05. It has further reduced the loss to 0.04, which is a fantastic performance if you ask me. Validation accuracy at this stage that we are getting is 98%. You can see here the images. We have 469 images. It has been able to build this model for 469. At this stage, I'm obtaining an accuracy of 98%. Let me see you in a bit. I'll wait for all the 10 epochs to get completed. So now, after about 10 minutes, the model has finally converged. And you can see here, we have run all the 10 epochs in this case. Look at the final validation accuracy. It is 98.7, which is not bad at all. We are obtaining a accuracy of 98.7 on the validation dataset. When you look at the accuracy on the validation loss value, the final value at the end of the 10th epoch was 0.04. So these are very, very interesting numbers and promising numbers that we have obtained after running a convolutional neural network on the MNIST data. The final accuracy on the validation sample is 98.7% and the validation loss is 0.04. Let's look at the progress of this particular model. In epoch 1, the accuracy was 97%. In epoch 2, it jumped to 98%. Further, it was stuck at around 98% itself. And after around 10 iterations, the final accuracy that it is reporting is 98.7%. Let's look at the validation loss. In the first epoch, it was 0.06, roughly around 6%, which through successive iterations, the model has reduced to 0.04. This is a good model that we have built to look at the final accuracy of the model. What you can do is you can run a model.evaluate function and feed it the necessary parameters of x_test and y_test. This will print the test accuracy. The test accuracy here is 98.6%, which is good. With this, I have come to the end of today's video. In today's video, we were working on the MNIST model. We have built a convolutional neural network with 6 different layers. We have learned how to predict handwritten images using a machine learning technique, and we were able to obtain a 98% accuracy. I thank you very much for watching this particular video. I request you to subscribe to my channel, also like and share my videos. Thank you very much once again. Have a great day ahead.